In this video, we're going to talk about divergence, curl, and the relationship between those two concepts that comes from Green's theorem. Or at least this is Green's theorem part 2, because in our previous video, we looked at Green's theorem part 1 that talked about the relationship between circulation and flux. Okay, so let's first look at what is curl and what is divergence. I'm going to begin with some vector field, and I have in that vector field a particular path. Now, this vector field is what I like to call a source vector field. You could, for example, imagine this was a gas and everything was sort of spreading away from the origin. Now, what we've previously talked about was the concept of the flux across this boundary. In other words, if I look at this curve that I have, the question is, well, how much is the vector field spreading across that curve? We compute this by taking the line integral of f dot n, where n is an outward normal to the particular curve. And the way I think about this is just adding up the tendency for the vector field to be aligned with the outward normal, and that gives the total flux. And for completeness, I'll just put up the formula that we computed in the previous video. If you have a specific parameterization, and you know your field can be described as m in the I hat and n in the j hat, then this can be computed by the integral of m dy minus the integral of n dx. Okay, now this was a global property around the entirety of the curve. But now let me zoom in. Let me zoom in actually right to the center. Now, I've still drawn this a little bit large, but I want to actually think of is that this rectangle is extremely, extremely tiny. It's looking just at the point, or at least in some tiny little rectangle around it. So if I want to have some notion of the degree to which the vector field is leaving away from that specific point, one way I could capture that is the degree to which there's flux over this tiny rectangle just around that point. Indeed, I could look at any other point. So for example, I could move over here, and this is sort of an interesting one. There's some vectors that are coming into it, particularly on the bottom and right-hand sides. And then there's some vectors that are leaving it on the top and left-hand sides. But because for this vector field, the arrows get longer as they go further from the origin, this means that the vectors on the left and the top side that are leaving are in fact longer than the vectors that are entering this little region on the bottom and right sides. So the point is, if you again imagine this being some gas, gas is leaving further along the top and left-hand sides than it is entering along the bottom and right-hand sides. So I still have a net outflow along this little rectangle, something in a few minutes we're going to call the divergence. Okay, so let me go and try to analyze this little tiny rectangle again. I'm going to blow it up even larger, and I'm going to imagine I start at some point x, y, and I shift over by an amount delta x and up by an amount delta y. My underlying field is m in the I hat and n in the j hat. Now, this picture may look familiar because in our previous video, when we were talking about circulation density or curl, we analyzed Now, this picture probably looks very familiar because in the previous video, when we were talking about circulation density or curl, we analyzed the exact same rectangle. And then we were asking the question of what is the circulation around it. Now we want to ask what is the flux outside of it. The computation is almost exactly the same, and it was a little bit long last time, so I'm not going to repeat it. I'm going to leave it as a challenge for you. So my challenge to you is to compute the flux around this rectangle and see if you can get it into the form, okay, I'm going to spoil the answer, so pause if you don't want to see it, into the form partial of m with respect to x plus partial of n with respect to y, delta x, delta y. So what is this formula showing? On the left-hand side, I have the flux around that small integral. That's what the integral of the f dot n ds does. The delta x, delta y is just the area of the rectangle. And so what I'm left with is this partial of m with respect to x plus partial of n with respect to y. And there's a couple different ways we can talk about that. One that makes sense is the flux density. So basically we're saying the total flux is like the flux density, the flux per unit area times area. That's one good piece of terminology. And the other piece of terminology is called the divergence. So the flux density is also called the divergence. And it is our notion for how much the vector field is spreading away from a point at some particular point, or at least in some small neighborhood around that particular point. Okay, so going back to our original picture, we have the global property, which is the flux around the big, large curve. And then if I zoom in on any particular point and imagine a very tiny rectangle around it, I have the divergence or flux density at some particular point, and it's given by the partial of n with respect to x plus the partial of n with respect to y. Okay, so now I want to ask, how are these two concepts connected? And indeed, we're going to see Green's theorem, part 2, is going to be that connection. It is going to provide this connection between this global property of leaving outside of a big curve and this local property of leaving around some particular point. Okay, so let me go to a generic region with a boundary curve C that is enclosing some region, and I'll call that enclosed region R. One of the things I can do is I can take this region and I can in fact cut it into two different subregions. There's a region on the left, whose boundary curve I'll call C1, and a region on the right, whose boundary curve I'll call C2. Then the following quite remarkable thing happens, which is the flux around the original curve, the big curve, is just the sum of the fluxes around the C1 and the C2, respectively. The reason why this happens is that, okay, if you take a generic n for the outside curve, the generic n vector, the outward normal, always has to be an outward normal, could just look something like this. But if I'm going to focus specifically on the cut, well, for the C1, the outward normal looks like this. It's going straight to the right if I've done a complete vertical cut. Whereas for the C2, at the corresponding spot, its outward normal is pointing exactly the opposite direction. So what that means is that everywhere you're on the cut, it cancels. And this just sort of makes sense. You're saying the amount of transfer of whatever it is, say a gas across the boundary in one direction, is exactly the negative of the transfer for the other boundary going in the opposite direction. Because these normals are just the negative of each other, any contribution along this cut is just going to cancel out. I can then cut more and more and more, so I've just done many, many cuts until I get smaller and smaller and smaller rectangles. And by the same argument, the flux around everything is just the sum of all the fluxes around all the little tiny little rectangles. And we know those rectangles, that's what we just studied. That was the divergence. The flux around one of those tiny little rectangles is just given by partial of n with respect to x plus the partial of n with respect to y, aka the divergence, multiplied by the little unit of area, delta x, delta y. And I love thinking about this as the velocity field for some compressible gas, because if I have two different little rectangles beside each other, the tendency for the gas to flow from the first to the second, well, now when I think about the second, just the negative of the tendency from the second to flow back to the first. Everything in the middle just cancels. And however much movement you have, the net accumulation, the net flux across the big boundary C, all that matters is how much is leaving that. It doesn't matter how much internal cancellation and how much internal movement there is. It just matters how much is flowing across the big outside boundary. All right, as we take our limit, as delta x and delta y goes to 0, what we finally get is going to be Green's theorem in its divergence flux form, or sometimes called its normal form. And it just says that the flux, that's what the left-hand side is, that's the outward flux, says the flux around the curve is just equal to the double integral of this divergence over the region. I have the same regularity conditions on my curve and on my vector field I've had before, and I'll just highlight again that it needs to be what we call a simple closed curve, and that basically just means the curve comes back and connects, so it sort of encloses a region, and by simple it means it has no self-intersection points, and that means that this curve that we have is truly enclosing one region that we can speak to. There's no ambiguities going on there. And then the final thing to reflect on is how, once again, this really can be thought of as analogous to the fundamental theorem of calculus, where we're talking about information around a boundary. For example, the outward flux is one measure of something that's happening on the boundary. It's the tendency for which the vector field is crossing the boundary. And that this can be written as an accumulation over the entire region of these differentials, this partial of n with respect to x plus the partial of n with respect to y. Much like in the fundamental theorem of calculus, like how when you integrate over a whole region some derivative, you get just the differences of the original function f of b minus f of a. But now we've upgraded. So we're talking about now some two-dimensional vector field, and we're saying along a curve, there's maybe two different things we're interested in. We might be interested in the circulation around that curve, in which case we saw Green's theorem part 1. Or we might be interested in the flux across that curve, in which case we're going to use Green's theorem part 2. But either way, it's relating some information that occurs along the boundary to a double integral over the entire regions of either, as we saw previously, a circulation density, or in this case, a flux density that we're also calling the divergence. Either way, a double integral over the entire region.